Hello everyone, welcome in a new video. In this video, we will discuss about contiguous memory management scheme. We discuss about contiguous memory management scheme. In a previous video, we discussed that the contiguous memory management is divided into two parts, single contiguous memory management and multiple partition. Okay, so first of all, we discuss about single contiguous memory management. We discuss about single contiguous memory management. Now, this type of memory management is used in a computer in a old days. Means uh, in a previous generation, the computer system is basically work on the single contiguous memory management. In this system, the main memory is divided into two parts. In this main memory divided into two parts, and these parts are equal. Okay, two equal parts the main memory is divided, and in one part the operating system is there. For example, this is what a memory. This is what a main memory is gonna look. Divided into two parts. One part OS reside always. In one part OS always reside permanently. Okay, and other part the process come and basically work and then terminate. So this is called a single contiguous memory management scheme. So OS is set permanently in one partition. Uh, in general, in general, if we talk about where in a memory, so if memory is divided like this, then at the lower part of main memory operating system is there in general. Okay, so in general, operating system reside permanently in a lower part of memory. Okay. So this is what basically a single contiguous memory management scheme process come and get the memory, do their work, then terminate. This is what a single contiguous memory. And you want to write, you can write it that the operating system reside permanently in one partition, generally at a lower memory. Generally at lower memory. Okay. And the user process basically load in the other part. This is what a single contiguous main memory. Now we are moving towards the important part, important type, which is multiple partition. Multiple partitioning. Now, multiple partitioning by its name, it is clear that now the memory is divided into multiple partitions. Means this is what we have a memory, and in the memory, partition is there now. Memory is divided into blocks. The memory is divided into blocks. These blocks are not always a fixed size. For example, like say this block is like 100 MB. This box is maybe 20 MB. This box maybe 10 MB. So the size of this main memory is not same. Okay, this is what multiple partitioning. Now, in multiple partitioning, it's further divided into two parts, which is called a fixed partitioning and a dynamic partitioning. Okay, they're divided into two parts, fixed partitioning and multiple partitioning. Let's discuss about, first of all, we discuss about fixed partitioning. Fixed partition, contiguous memory management. Okay, so now what happened in the fixed? The main memory is divided into several fixed size, and fixed size, or you can say the fixed partition, in which fixed partition memory management. uh, for example, let's, with the help of example, let's understand. This is what a main memory. Main memory divided in a fixed partition. Fixed partition doesn't mean the memory available on this is fixed. Means If this is a 100 MB block, this will be a 100 MB block. There is no shifting of size take place. Okay. These partition can be of same size or maybe of different size. For example, 100 MB, 100 MB this block as well. 20 MB this block means same size partition will be there and different size partition will be there. Okay. Each partition can hold a single process. This is very important point. Okay. Each partition can hold a single process. Single process. Each partition can hold only a single process. Let's say P1 is a process, so P1 will reside completely in a first block. P1 reside completely in a first block. This is what the meaning of a fixed partition. Okay. Now, the number of partition determine the degree of multiprogramming. Means if there is a 10 partition, then 10 is a degree of multiprogramming. Means 10 process can reside in a main memory, and 10 process can execute at a particular 10 process can be executed. Okay. So the number of blocks number is equal to the degree of multi-programming. Next, these partition are made at the time of system generation and remain fixed after that. When system is generated, the partition is there. The partition is made at a generation of a particular system and it always same. Okay. So these are the fixed partition concept. I hope you understand this thing. Now, the important point, which is that in this case, the operating system is on the top. The top block is basically operating where the operating system resides. In a top block, operating system resides. Now, we understand about fixed partition. Now, there is a concept called internal fragmentation. What is internal fragmentation? Now, what is internal fragmentation? In internal fragmentation, when space is allocated to a particular process more than it's required, more than it's required, then the remaining space, the extra space, is basically wasted, and that wasted space is called internal fragmentation. What does this mean? This means that we have a main memory. We have a main memory of 4 partition. Let's say 200 MB space was in this block. P1 is a process. P1 is a process which basically need 100 MB of space. P1 is a process which need only 100 MB of space. But due to contiguous memory allocation, P1 is allocated to this block. P1 is allocated to this particular block. Now, the extra 100 MB space, because P1 only need 100 MB. So 100 MB is utilized. But in this block, there is 200 MB space. So the 100 MB extra space is called internal fragmentation. The extra 100 MB space is called internal fragmentation. So if you understand what is an internal fragmentation, so when a space allocated to a process is more than it's required, then the extra space is wasted, and that waste space, that waste of space is known as internal fragmentation. That waste of space is known as internal fragmentation. So I hope you understand about internal fragmentation. Now, after internal fragmentation, let's understand that how basically the process is basically allocated to a particular memory. For example, we have a main memory and we have main memory divided into some blocks. Now, how, let's say we have 6 process P1 to P6, how P1 to P6 is allocated to this block We see this thing. Okay. So how partition allocation policy work, we see this thing. Partition allocation policy. Okay. Now the first one is called first come first serve. Oh, sorry, first fit. This is called first fit. Now what does this mean? This means that if P1 come, let's say P1 to P6 come at 0, 1, 2, 3, 4, 5, 6 of it, 5. Let's say that P1 to P6 process are come in a that sequence. Means first of all P1 come, then P2, then P3, then P4, then P5, and then P6. So those process who come first get the memory first. Doesn't matter what the requirement of the memory for the particular process. For example, let's say this is 200 MB, 100 MB, 50 MB, 500 MB, 250 MB. If P1 need only 50 MB space, doesn't matter. If P1 come first, P1 allocated to that particular first block. If then P2 come, then P2 allocated to the second block. Those who come first will get the memory first. So it means that the first partition from starting store the process which allocate basically. So those processes come first, get the memory first. Okay, so that's easy. There's no need to write about it. Now the second is called best fit. Best fit. Now, what is a best fit means? Best fit means that if P1 is a process that need 50 MB of space, P2 is a process that need 500 MB of space. Let's talk about these two processes. So P1 doesn't, so P1 is not, P1 basically need 50 MB of space. So P1 goes to that block which is of 50 MB of size or less than 50 MB of size, so that there is a very small wastage of memory. Okay, P1 need 50. It check if there is a 50 space, 50 MB space there, any block of 50 MB size. If it find, then P1 will go there. Similar. If P2 need 500 MB of a space, it check 500 MB is there. So definitely one block. So P2 is allocated to that block. This is called best fit. Okay. Now the third one is called worst fit. By its name it is clear. Worst fit. By its name it is clear that it gonna do the worst. Means if like P1 need 50 MB, so it find that place. Okay, so it find that place where the maximum memory is there. So every block is empty. It find that the operating system find basically there is a block size of 500 MB and we have a process of 50 MB. So what it does in a worst fate, the P1 process assigned to that memory which having a very high memory. Okay. Uh, Now that process will go to that block which have a very high memory. Okay. So P1 goes to P2. Regardless, P1 can go to the first block, second block, third block, fifth block, any block, but it goes to that block which have a very high memory space. Okay, this is called a worst fit. Now the fourth one, or you can say last one, is called a next fit. Now what does this mean? This means that let's say we have a process P1 which need 50, P2 which need 250, P3 which need, okay, so P2 let's say we need 450 and P3 which need 200. So what next fit says? Next fit started from the first part. Let's say P1, because P1 is a process which comes first, so P1 is allocated to first. Now, in a next fit, what happened is P1 check that if there is first block, if there is a space, And yes, there is a space. So P1 reside there. P1 reside there like first fit. Like first fit. P1 reside there. Now in the second case, P2 need 450 of space. So it's check second block. It check second block that what's the space 100 MB. Definitely not able to reside this. And in third, it needs the space is 50 MB. Definitely uh, not able to access this space. Now the third one is 500 MB. So P2 allocated to this part. P2 allocated to this part. Then P3. Now, what the next bit says, where you leave the process, the next allocation of memories is started from the next next block of that particular process. Now, in a starting point, a cursor is here. P1 is in first block. P2 we check for the memory after the P2 after the P1 block. P1 placed at first, then we check next block for the P2, next block for the P2, next block for the P2, P2 reside there. Now P3 let's say need 100 MB. You cannot place P3 over here. You cannot place. This is called first fit. This is called first fit. You cannot do this. What you have to do is you have to check the space next from the previous process which you allocate the memory. So the previous process is what P2 allocated to this block. Now you have to check this block, the next block of that particular process. So P3 need 100, 250 space. P3 can easily reside there, so P3 can get. Now let's say P4 is a process which need 100 MB. So now you can start from the start. This is how the next bit works. Where you leave the process, next process memory allocation will be started from that next part. Okay, so this is how the partition allocation. This is how the basically the memory allocation will work. Okay, question, and we are good to go for the next part. Okay, so we have a processes. Let's say we have a processes P1, P2, P3, P4, and P5. We have a 5 processes of size. P1 is a process of size 150 MB. P2 is a process of size 400 MB. P3 of 270. P4 of 180, and P5 of 50. Now, what you have to do is you have to apply the fit, first fit, best fit, and the worst. Okay. Now, the space of main memory is look like 100 MB, 250 MB, 200 MB, 500 MB, 300 MB. Okay. So these are the these are the 5 spaces, and these are the memory. Now, what you have to do is uh, you have to add this. What you have to do is you have to add this process. That's it. Okay. These are the block size. These are the block size. Now, first of all, you have to apply the first two. P1 is a process who come first. So, what is basically the memory? So, I write like this so that there is no. Okay. So, now we're gonna apply first bit. We have to apply the first bit. Okay. So 150 start from the starting. 100 MB definitely P1 process not able to access this part because this is less than what it needed. Second 250 definitely P1 able to access. So if it is able to access in first bit, then it will. Okay. So 250 memory, this part is goes to P1. Okay. Now second is 400. This is the first bit we have to start from the starting. Now, first block 100 MB definitely not able to access. 250 not able to access. 200 not able to access. 500 yes. For P2 process will get 500 of memory space. 500 MB of memory space. P3 process start from the starting. Now this part is okay. So uh, now this part is allocated this. This part is allocated. Two part is allocated. Now the third one is P3. Start from the starting 100 MB, 250 is needed, definitely not able to access. P4 180, oh sorry, P3 now moving towards the next block which is 200, definitely not able to access. Then the block left which is 300. So and P3 able to access this block because block size it needed memory of 270. Here the memory is 300. Definitely this block is access to the P3. Now the last block is also allocated. Two block left, 101 and the 200. Two process left. P4 180 needed. Start from the starting. Start from the starting. 100 MB definitely not able to access this part. 200 MB definitely P4 will get this block of main memory. Okay, so 200 will get to P4. P5 one part left which is 100 and the process size is 80. P5 get this block. So 100 MB goes to that. What is internal fragmentation? Means the wastage of extra space. 100 is the main memory size. Process need 80 means 20 MB is a wastage. 20 MB is a internal fragmentation. Okay. Now this is called first fit. Now we are moving towards the best fit. What best fit says? Okay. So now we remove this. Now we start from the start. Okay. Now best fit process where less internal fragmentation there. Or we are going to add that process to that particular memory where less internal fragmentation occurs. P1 process 150. Let's see that 101 definitely not able to not able to access this because the process size is 150, the block size is 100. Second is 150. We can apply, we can basically P1 can allocate this 250 MB of space, but we are not gonna do this because there is an internal fragmentation of 100 MB. 150 process needed, 250 is a size. So if you subtract this, you will get 100 MB of wastage space, or you can say the internal fragmentation. So we cannot do that. This is the best fit. Less internal fragmentation. We have to choose that block which is having a less internal fragmentation. Second, let's say we go to the third, we go the fourth one, which is 500 MB. So definitely you cannot do that this as well because there is a 350 MB of internal fragmentation. You cannot do that as well. 300 definitely you cannot able to, you cannot do this because it's the best fit and you cannot do that. There's a 150 MB of internal fragmentation. Better to use 250 rather than 300. Now we have one block which having a 200 MB of space. So 200 minus 150, you will get 50 MB of internal fragmentation. You get 50 MB of internal fragmentation. So which block having a less internal fragmentation, we provide that space to that particular process. So 200 MB goes to P1. 200 MB goes to P1. So I hope you understand this thing that how we allocate this space. Okay. So let's remove this for the next process. Now P2, which is a 400. Now this part is allocated. P2 400. So in 101, definitely not able to reside, not able to reside in 250 as well. 200 already filled. 500, yes, we can provide this, we can allocate this memory to P2 because there is only one block which can able to provide memory to that particular process because there is a 300 less than 400 memory is less than the process size. So definitely only one block left which is 500. So 500 is also allocated to P2. P3 270. So 270. Now similar case 101 we cannot provide this space to P3 because the size is less than the process size. So we cannot do that. 250 and 300. We choose that block which gave a less internal fragmentation. So 301 gave more internal fragmentation. Here the internal. Okay. So this is 270 and there is 50 only one block left which is 300. So definitely P3 will goes to 300. Because 250, the process size is 270. Only one block left, the last one, so that block is there. P4 180. Now two part of block left, 101 and 250. Cannot reside on the first block, so definitely second block allocated to second 250 memory space is allocated to P4. So 250. Now for P5, 81 block left. So and able to access that, able to allocate this block. So 100 MB allocated to P5 block. Now we're gonna do the worst fit. We have to do the worst fit. Worst fit says that highest internal fragment. Worst fit says we need high internal fragment. So let's say P1 process 150. Worst fit choose that block which having a very high space. So among all these five blocks, 500 MB is the largest space. So P1 get 500 MB in a worst fit. So what's the memory internal fragmentation here? If I have to calculate the internal fragmentation, so what's internal fragmentation is 500 minus 150, which is 300 MB of internal fragment. Highest internal fragmentation in a worst fit, in a best fit, less internal fragmentation. P2, 400 definitely cannot access any of this block because there is only one block which can able to get P2, which is the block number 4, but that is already allocated to P1, so definitely P2 doesn't have anything. Okay, I remove this. So P2 does not have anything and 500 is allocated. Now P3 270, highest one is 300, so 300 can able to get this, so 300 MB will get to P3. 300 is also allocated. Now the space left is 100, 250 and 200. P4 180. We choose that process because it can reside on the second block and the third block, but we choose that block which give a highest internal fragmentation. So 250 give a highest internal fragmentation, so 250 allocated to P4. Right? Now 80, we choose that process which give highest internal fragmentation. We can reside P5 on first block, 100 MB block, but we cannot do that because it gives less internal fragmentation. We need worst. So 200 MB of space is allocated to P5. So this is how we can solve this question. So I hope you understand that how we solve this question, how the best fit work, worst fit work, and how the first fit work. Okay, now you can write like that. If you want less internal fragmentation, then you have to use the best fit. So it means that best fit works better in fixed partitioning or fixed partition. Okay, best fit work in a fixed partition, contiguous memory. Okay, so I hope you understand this thing. Now we discuss about we discuss about the internal fragmentation and the fixed partition. Now the next concept is called a dynamic partition. We see dynamic partitioning in the next video. Hello everyone, welcome in a new video. In this video, we are discussing about the dynamic partitioning. We already discussed about fixed partitioning. Now it's time to do some variable partitioning or dynamic partitioning. Dynamic partitioning is also called variable partitioning. Okay, why we say it variable, why we say dynamic? Because here the main memory, in this case, the main memory, the space allocated to the processes is variable. Process, let's say that P1 need 50 MB of space. So in dynamic partitioning, main memory allocate 50 MB of block to the P1 process. Okay, that's how we say dynamic partitioning means the process need that much. If a process needs 50 MB, 50 MB is allocated. Whatever the memory needed for that particular process, that memory is allocated to that process. Okay, that's why it's called dynamic partitioning. That's and let's say that P2 which need 20 MB of space. So what it does, P2, what main memory does, main memory allocate 20 MB of block to P2 process. Okay, that's why it's called a dynamic partitioning or a variable partition. Now, it was basically designed to overcome the problem of fixed partitioning, because in fixed partitioning, there is a fixed space. So if a process is of 50, let's say that this is what a main memory, and if a process P1 is of 20 MB and the block size is of 50 MB, because it's a fixed partitioning, and fixed partitioning, the space is already predefined. So if a process there is only one process P1, and if it use first fit, if it is used first fit, then definitely P1 come in that particular block, and and the, because P1 only need 20 MB of space, here 50 MB means the extra 30 MB is 30 MB of space is waste. Extra 30 MB of space is waste, and that waste, basically that wastage of that space is called internal fragmentation. So to overcome internal fragmentation, we have a concept called dynamic partitioning, where main memory, basically operating system, allocate that much of space which needed for the process. Okay, so whenever a new process arrives, then a new partition which is equal to the size of a process is created and it allocated to that particular process. So you write it like, whenever a new process is arrived, then a new partition equal to the equal to the size of process is created and is allocated to the process. Okay, this is what happened in a dynamic partition. This is what happened in a dynamic partition. Let's take an example. Like we have a main memory. This is what a main memory, and let's say the size of a main memory of 600 MB. Okay, whole size of a main memory is 600 MB. Now, what happened? A new process is created. Let's say the new process is P1. New process is P1 which is created, and the size of P1 is 250 MB. Let the size of P1 is 250 MB. Now, what happened when P1 basically need 250 of space. Now, what happened? The operating system allocate 250 MB of space from a main memory. Now the space is basically created for the particular process. Fixed partitioning, space is already created. That's a main difference between these two. Okay, so now 250 MB of space is created for the P1 process. Okay, so from empty, there is no block. Now it have one block of 250 space. Now let's say that let's say that P2 is a process, the second process P2, and the size of P2 is 150 MB. Size of P2 is 150 MB. Now what happened? Here only one block in a main memory right now. Now when other process, the second process P2 is come, what happened? Now other space of 150 MB is created and allocated to P2 process. Allocated to P2 process. Okay. When process arrive, then main memory create a space for that particular process. It's not predefined. It created instantly when the process needed. And let's say that P3 process, third process come, and the size of the process is 100 MB. What's the total size? 250 and 150, 400 MB is already occupied. Now the space left is 200 MB. Now P3 is a process which need 100 MB of space. Now what happened in this case? This is what a main memory. 250 allocated to P1, 150 allocated to P2, and there is a third process which need 100 MB of space. So 100 MB is created in a main memory and allocated to P3. Now the space left in a main memory is what? 100 MB. Okay. So this is how the dynamic partitioning works. Process arrive, If process need this process need 250, then 250 is created. Whatever the need of a memory, main memory allocate that space to the particular process. Okay. In this case, worst fit work better in variable partition. Okay, if you are using dynamic partitioning or a variable partitioning, then worst fit work best. Work better in variable partition. Okay, in a fixed partitioning, best fit work best, but in dynamic partitioning, worst fit work best. Okay, in this case, there is also the wastage of memory. There is also a wastage of memory, but the wastage of memory in this case is called external fragmentation. What does this called? External fragmentation. External fragmentation. Here, in the above example, the 100 MB of space is left or 100 MB of space is waste. Then this wastage of space is called external fragmentation. Okay. When all process occupied the space and the space left in a main memory is called external fragmentation. Okay. Now, let's see the example of an external fragmentation. Here we have a main memory, and one part is occupied, let's say for the P1. There is an empty space here, means if a process need a space, that this space is allocated the to that process. Okay, and let's say that P2 process is also occupied this space. Okay, and these two space are empty space. Empty space. Now, empty space is also called holes. If in a question holes is basically written, it means it determines the empty space in a main memory. Okay, so in this case, and let's say that this needs the space of this part is 150 MB and the space of this part is 100 MB. Okay, now what happened is, what meaning of an external fragmentation? We have three processes in our system, P1, P2, and let's say P3. P3 need 200 MB of space. P3 need 200 MB of space. Does P3 get the space in this main memory? So our answer is no, because this block is of 150 size and the last block is of 100 size. So there is a no block of 200 size. So definitely P3 not able to get the space. But what happen if these empty spaces are assigned in a one side and all the filled space are assigned in a one side? What I'm going to say is that what happen if P1 is allocated like this, and then just after P1, P2 is allocated, and these two blocks are here, 150 MB and 100 MB. And now P3 comes, because it's a dynamic partitioning, it's a variable partitioning, it means we can adjust the blocks. We can give a memory to that process, whatever the memory it needed, we can give that memory if main memory have that much of space. So if now P3 need 200 MB, and here the collection of these blocks are what, 250, 200 needed, 250 we have. Now we can provide P3 to these blocks. Now P3 get the space in a main memory. Okay, here we cannot give that space because it's only 150 and other process is already using this space, so we cannot shift it and 100 MB. But if we can shift by any method, if we are able to shift these space, then there is a less internal fragmentation, and this wastage of space, because this is not used for any processes, because we have three processes needed 200 MB. So definitely this process cannot, P3 cannot use main memory. So this space is waste. So this waste of space is called external fragmentation. And the solution of external fragmentation is, by any chance, if we aside the already occupied space and the free space, and then we can use that free space then we can overcome this external fragmentation. Okay, so I hope you understand about the external fragmentation and the solution of external fragmentation. Okay, now this solution is called compression. Okay, compression means we compress these occupied space and unoccupied space side by side. Okay, so uh, when we are using dynamic partitioning definitely suffer from an external fragmentation. Dynamic partition is a solution of internal fragmentation, but it suffer from an external fragmentation. And the solution of external fragmentation is to avoid basically compression. We need to collect all the allocated process side by side. Okay, so this is what the compression problem. This is also not known as compression problem, and the solution is this, by moving the occupied space and unoccupied space side by side. Okay. So I hope you understand about the external fragmentation, you understand about the compression problem, the solution of a compression as well. Now, there is one more thing in compression, that if operating system do this thing, means operating system, if doing this stuff, means occupied space one side and unoccupied space from other side, so basically it take a lot of time. If p1 and p2 are side like this and empty space are side like this, it take a lot of time to do this, thing. Because in our main memory, here we have only 4 blocks. In a main memory there are thousands of blocks, so it take a lot of time to shift in the memory, and we are not having a lot of time, so definitely this solution is not useful. It decreases the efficiency of the system. Okay, so we are not going to use this solution in a real world. In a real world, the solution of external fragmentation is paging. This paging concept is used to solve this problem. Compression, we are not basically solve the problem of compression. We are not making the process side by side. Okay, because it take a lot of time to do that. Operating system take a lot of time to process these things, because first of all you need to identify which spaces, which space is filled, and the process need how much space, then it making a side by side processes, memories, so it take a lot of time, and the efficiency of system is affected, so definitely we are not going to use this thing. Okay, the solution is of external fragmentation is, real world solution is of external fragmentation is paging. In paging, we divide this block into so many other block, and so many other block are further divided into block. When we discuss paging, we discuss this solution. Okay, now we understand so many things. Now it's time to solve a question of variable partition. Okay, so now consider a variable partitioning in a main memory where you have 4 holes. Holes means empty space where you can put your process. Okay, so 4 holes, and we have 250 MB, 200 MB, 500 MB, 500 MB, and 400 MB. So we have 4 holes. This is like 4 holes. Now you have a process request, and these requests are, let's say, the process P1, P2, P3, P4, P5, and P6. Let's say 6 processes we have, and the size of these processes are 150. All are in MB. Okay, 400, 270, 180, 80, and 50. And these are, we have an empty space. We have a processes. Now what you have to do is you have to provide that process which are stored for first fit, best fit, and a worst fit. You have to perform first fit allocation policy, worst fit, and the best fit. Okay, so I hope you are, it's an easy thing, you can do that. So let's solve this question. Pause the video and try it by yourself. And now let's solve the question. Now it's a dynamic partitioning. First of all, 4 holes. Let's say that this much space is of 250 MB. Then we have a block, okay, which is already filled by some processes except these 6. Okay, So we cannot use this space. Okay, we cannot use this space. Now, after that, this block is of size 200 MB. Then again, already filled block. Then let's say that we have this part of 500 MB of size, and this part is of 400 MB of size. Okay, so we have these four parts. Now you have to perform the best fit, worst fit, and everything. Right? First of all, what we are going to do is we are solving this thing by first fit. So first of all, try it by yourself. Try it by yourself, and then pause the video and try it by yourself. Now let's solve this question. First of all, we have the processes P1 which need. We are going to solve this question by first fit. Okay. So which process come first will get the space. P1 need 150 MB of space, and we start from the starting. This is a starting point. Okay. Now P1 need 150 of space. We have 200 MB of space, so definitely P1 occupied this. And the space left is 100 MB. 100 MB of space is left. Okay, because P1 occupied 150. Okay. Now P2 process. Start from the starting. Here 100 MB of space is left. Does P2 can get this space? So the answer is no. P2 need 400 MB and we have only 100. Definitely not. P2 cannot get this space. Now move to further. 200 of block. Can P2 occupy this space? So answer is again no. 200. P2 needed 400. Cannot able to get this space. Move to the other block. 500 MB of space. P2 need 400 MB. Can P2 get this? Answer is yes. So in first fit, if a process get a space, it get that space. So P2 occupied 400 of space from this side, and the space left is 100. P2 can get on this block as well, the last block, but for which space come first, process get that space. Okay, so in the third block, P2 occupied space. Now P3 start from the starting. Okay, 100 MB of space left in this block. Definitely P3 not occupy this space because P3 need 270 and we have only 100. In the second space, we cannot, same thing, limited space. P2 P3 need 270, we have only 200. And the third block 100 space, P3 need 270. Definitely we cannot build this. And now the last block 400 MB of space, and we have P3 of size 270, so definitely P3 will get this. So 270, P3 will get this block, and the space left is 130 MB. Okay, 130 MB of space is left. So P1 is completed, P2 is completed, P3 is complete. Now it's time for the P4. 180 of space. Start from the starting. 100 MB cannot occupy this space. P4 cannot occupy this. Now on the second block, 200 MB of space and P4 space is 180. So definitely P4 get this space 180. Now the space left is 20. 20 spaces left. Okay. And P4 is also completed. P5. Start from the starting. 100 MB of space we have. P5 need 80. So definitely P5 get this. And 80 space is occupied. Now the space left is, okay, so the space which left is 20. So this 20 space, this is 20 MB space left. Okay. Now P5 is also completed. P6, 20 MB of space left, we cannot put here. And the second block we have 20 space left, 20 MB, we cannot put that thing as P4, P5, sorry, P6 in this block as well. And the third block we have 100 MB of space and P6 need 50, so definitely P6 get this space. So P6 50 MB needed, and we have that space, so we filled this with P6. Now the space left is 50 MB. Okay, 50 MB is left, and we completed all the processes. We completed all the process. Okay, so if all the process complete, now calculate the external fragmentation. Calculate the external fragmentation. So here 130 MB of space is left. Here 50 MB. here 20 MB, and here 20 MB as well. So 50, 5, 6, 7, 8, 180 MB from last two blocks and 40 MB from the last two blocks. So it's 220 MB of external fragmentation occur in first fit. Okay, so I hope you understand that how we solve this question. Now, this is what a first fit. Now let's solve this question by best fit. Okay, so let's solve this question here. Okay, let's solve this question. Okay, so start from the starting. 150 it needed. Best fit, so which space is basically aligned to that process, we provide that space to that particular process. Okay, so P1, 150 needed. First block 250. We can put this process here, but we are not going to put this because we are finding first of all the process, the space which is equal to P3 needed space or just as closed as possible. So 250 is very far, 200 is close to P1, but now let's check for the other two block as well. So 500 and 400 very far away, so definitely P1 get space in the second block. Okay, so P1 150 space is get in this block, and the space left is what, 50 MB. 50 MB of space is left, and P1 is complete. P2 400 needed, so select from first block, no. Second 150, no. Equal to P2 needed or as close as possible. 500, not very far away. 400 it has 500, and the last block 400, and P2 needed 400, so definitely P2 occupied here, and there is no space left in the last. Okay, P2 is also complete. P3 270, first block 250, definitely we are not able to add this process here. 50 not able to add. 500 only space left, and if only space left, then we have to provide this space to that process. So 270 space is filled here, and the space is left is 230. Okay, 230 spaces left here. Now P3 is also completed. P4 180 needed. Start from the starting. 250, 180. We can put this process, but we are not going to put this because it's a very far. It's not close. The memory space is not even equal to or not even close. So we cannot put it. So in the second block, 50 space left. We cannot able to put this. In a third block, 230 spaces left, and it's a 180. So if we compare first block and a third block, so we definitely have to fill this in a third block. So 180 space here. Okay, so we put 180 over here, and the space, we have space left, so 230 and 80, 50 MB of space is left here. Okay, so 50 MB of space is left in this side. Okay, now P4 is also completed. P5 80 MB. First of all, start from the starting. We can put P5 in the first block because in the second block we have 50 MB of space, and the third block we also have a 50 MB of space, so we cannot put that. So P5 get this space. So 80 MB. So if you subtract 80 from this, you will get 250 and 80. So you will get 70 MB. Means 170 of space is filled, is left basically. P5 is also completed. P6 50. So we can put any of the middle two blocks. So let's say I put it P6 over here. So 50 MB is now filled. 50 MB is now filled. So now let's calculate the external fragmentation. Let's calculate the external fragmentation. So in this case, 150 MB of space. In this case, 170, and addition of 50 MB. So here the external fragmentation is 220. The external fragmentation is 220 MB. Okay, so we solved it by best fit. Now it's time to solve it by worst fit. Okay, so now what can we do is here. Now let's solve this by worst fit. So let's solve it by burst fit. Okay. First of all, we have a process P1. Okay. So right now it's not number. P1, 150 of a space, which having a very high space, we have to put this process there. This is what the burst fit says. So very high space is the third block basically. So we have to put P1 over here. 150 needed, 5 we put it in a 500, so a lot of space is left here. And the space left is what? Uh, Here the space is 150, it means 0, 5, and 4, 3, 350 of spaces, 350 MB of spaces left. P2, 400, very high space. We cannot put on first block, second block, third block. There is only one block left, so definitely we have to put P2 over here. So now fourth block is fully filled. Okay, no space left. Now P1 is completed, P2 is completed, P3 270 needed, the highest space block, and the highest space block is the third block 350. So we have to put P3 over here, and P3 is of 270 of size. So the space left here is 80 MB. Okay, so 80 MB of space is left. Now P3 is completed. P4 is turned for the P4, 180 needed. First of all, see the highest block. So it's the first block which having a very high space. So P4 needed 180, and definitely we have to provide P4 over here. So 180 it needed, and the space left is 50, 60, 70 MB. 70 MB of space is left here. Okay. Now the second is P5 80, which is the very high space, only the third block. So P5 get here 80 MB, and the space left is 120 MB. Okay, so P5 is completed. P6 50 needed, very high space, very high space. This one, in a second block. So P6 get space in a second block, which is 50. Well, so the space left is 60 MB. 60 MB of space is left. So now let's calculate the external fragmentation in verse fit. Okay, so 70, 60, 80. So it become 8, 21. So 210 MB of space is waste, or you can say 210 MB of external fragmentation there in a verse fit. So let's check which allocation policy work better in a dynamic partitioning or variable partitioning. In a first fit, we have an external fragmentation of 220. In a best fit, we also have an external fragmentation of 220, but in a worst fit, we have an external fragmentation of 210. Okay, 210. So definitely work better in dynamic partitioning or a variable partitioning. So I hope you understand this question, understand all the dynamic partitioning concept, external fragmentation, compression, problem of compression. Okay, so this is what all about the contiguous memory allocation. Okay, so if you want to know about the non-contiguous memory allocation, then click on the next video.